concentration unit. So if I'm talking about P sub A, RT, right? Because it's moles of A over the volume. The volume of A, but all the gases have the same volume. That's one of the arguments I made a few minutes ago. But it still gives you the concentration of A in moles per liter. Oh, look at this. That's not the one I'm going to look at. I'm going to look at the easy one. I'm going to say, here's my gas phase equation. I'm going to write P sub C, P sub D, D. Mostly because I don't want to fool around with the algebra too much. Everybody says, okay, this is going to be called K sub P. I had it here a minute ago, but I erased it because I just left the original thing here. And I want to go, this is called K sub C, so I want to go from here to here, or vice versa. The reason I wanted to write it like this, it makes my algebra easier. Because P sub A, what can I write here? Since I have it there, I'll say P sub A, concentration of A, small a, R, T, parentheses, small a. What am I going to write for P sub C? Yeah, it's the same formula, except I substitute in the different exponents and things. Concentration of C, small c power, RT, small c, and in the denominator I'm going to have concentration of B, small b power, small b. I'm going to factor this, 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 and this out, and I'm going to factor out the RTs. Okay. So what I started out with was this thing, which was K sub P. I made a bunch of substitutions. What I'm going to end up with is and I'm factoring out RT. How do I factor out RT? Going back to algebra 2. Right? Because when I multiply things, I add exponents. When I divide, I subtract exponents. That's why I said we're going back to algebra 2. You learned that a long time ago. Or you had to pass algebra. I don't know yet. Because there are other things that he taught me. So maybe that was 20% you didn't have to know and you still got a B. Whatever. Now you have to know it because I just used it. But the result that you're going to use is really, I started here with K sub P. And this is in the book, by the way. Delta N. This is the moles of gaseous products minus the moles of gaseous reactants. Delta final minus initial. Products are final. Reactants are initial. So that's change in the moles. Okay. So that's the relationship between K sub P and K sub C. When people say, how do I always remember it? And probably the easiest thing to think about, pressure, K sub P, K sub C, RT to the delta N power. Because this is the equation we're going to use. This is just justifying why I'm going to write that equation. And one of the things we do a lot of times in this course, we have a final equation which you actually use to solve problems. And all the rest of it is just proving why you got to that equation. So I told you how you got to there. You can remember that for whatever it's worth. But this is the thing you have to use. Now notice I'm talking about the H2I2 problem, this thing. How do we relate this number to K sub P? C number, and I want to calculate K sub P, or vice versa. You say, okay, I did it. Am I right? Yes, I am, because delta n is 2 minus 1 minus 1 is 0. RT to the 0 power must be 1. So K sub P and K sub C are the same number for that particular reaction. On the other hand, if I have a reaction like this, all of these are gases again. How are K sub P and K sub C related? I'll work with my basic formula. It says K sub P RT to the what? 3 plus 1 minus 2 is squared. Now the thing is, when you put in R, we're going to see a lot of different R's right now. Since we're working with gases, we'll use the one with atmospheres. And he hasn't changed his problems yet, but remember, we talked about this in 1A. I don't know if those of you had other instructors, whether they mentioned it too much. But one of the things we're switching over is the standard state definition. In the old days, the standard state used to be 1 atmosphere, 273 K. In the new days, standard state is 1 bar, 273 K. So what we should do, if everything were really up to date, is use R in terms of bars rather than atmospheres. But all his problems, actually I didn't solve every one of his problems in the textbook here, but I think he always uses I rounded off to 3 if you like, 0.08206. That's fine. This is liter atmospheres. I'm sure he spent a lot of time with that. So he's working with pressure units of atmospheres. So I think he still uses that number throughout his textbook. He changed some of the things in the gas law chapter, but he didn't change any of the other chapters yet. At least not that I know. As I said, I didn't solve every single problem, but I looked at 1 or 2 of them, and he still uses that. And then the temperature, of course, is expressed in kelvins. We always do things in kelvins when we're working with gas laws. So if you know this number, you can calculate this, you know the temperature, and then you can go to K sub P by just multiplying. If you know K sub P, you divide by that factor. That's the reason I didn't want to start with this, because I would have had a reciprocal RT with the minus this, with the denominator minus the numerator, and I wanted to write it the way we always do delta n, as products minus the reactants. Okay. So that's one of the problems, going from K sub P